Welcome to Study Loop.
We have a three-dimensional box. We're trying to maximize its volume. Maximum, here, find maximum of V equals XYZ, volume of a box. Okay, and what we know about this box is that the length of the diagonal going from, let's say, the top front corner to the back bottom corner. Okay, the length of this diagonal is L. Okay, given that, or the constraint is, all right, so we have to write an equation for the length of this diagonal, which I'm going to call D for a minute. So first tell me how to find this one down here. Well, remember this is a box, so this is a right angle. So x squared plus y squared equals this one down here, r squared, or whatever you want to call it. So then if you know this one, then you can add this one in, because that's also a right angle. So r squared plus z squared equals d squared. So x squared plus y squared plus z squared equals L squared, L squared. Okay, that's our constraint. That says this will restrict the answer from being infinity, because if there was no constraint or restraint on it, the answer would be the maximum volume of a box is infinity. So this is limiting the size of the box. Okay, so now what we have to do is we have to do what we always do to find the maximum of something. Take the derivative, set it equal to 0. Okay, but we have too many variables, x, y, and z. That's why we have this constraint. So let's use it and get the z out of there. So z is the square root of L squared minus x squared minus y squared. So v is xy square root of L squared minus x squared minus y squared. So in fact, we're going to take two derivatives and find where they're both equal to 0. So let's do v sub x first. This will be my first, and the square root will be my second. First times the derivative of the second plus the second times the derivative of the first. Okay, remember x was the variable, so y is a constant, so the derivative of xy is y. Also, this is a square root, so its derivative was 1/2 the stuff to the minus 1/2 times the derivative of the stuff. Okay, I'm going to do some simplifying here. This 2 and this 2 cancels and leaves me minus x squared y over the square root of L squared minus x squared minus y squared plus y times the square root of L squared minus x squared minus y squared over 1. So now get a common denominator so you can add them together. So I'm going to multiply the top and bottom of this by this square root over here. So I get minus x squared y plus y times L squared minus x squared minus y squared all over the square root. So we get minus x squared y plus L squared y minus x squared y minus y cubed all over that square root. So minus 2x squared y plus L squared y minus y cubed over that square root. Okay, that's Vx. Now I'm not going to go through and do the whole thing again for Vy, because the only difference is that x and y are just going to switch places. Whatever was the derivative with respect to x is now whatever. Okay, so like here, where I have minus 2x, I'll put minus 2y. And here where I have y, I'll put x. Everything else will be exactly the same. So then what will happen in the end? Well, it will look exactly the same except for the x's and y's will be switched. So Vy will be minus 2y squared x plus L squared x minus x cubed over the square root. Okay, work it out if you don't believe it. All right, now I'm going to set each one of those equal to 0. So I don't care about the square root on the bottom. That's why I'm just ignoring it. Okay, on the first one, I'm going to factor out a y. And so I have L squared minus y squared minus 2x squared equals 0. And then on the second one, I'm going to factor out an x. And I get L squared minus x squared minus 2y squared equals 0. Okay, so this tells me y equals 0, or L squared minus y squared minus 2x squared equals 0. Well, certainly y doesn't equal 0, because if it does, then there wouldn't be a box. Same thing over here, x can't be 0. So we get this. Okay, so now we just have to figure out how to solve this system of equations for x and y. I think I'm going to multiply this one here by -2 and then add it to the other one. So I have -2L squared plus 2y squared plus 4x squared equals 0. And this one is L squared plus 2y squared minus x squared equals 0. Oops, minus right here. L squared minus 2y squared. Okay, add them together. And I get minus L squared plus 3x squared equals 0. So 3x squared equals L squared. So x squared equals L squared over 3. So x equals L over the square root of 3. Okay, instead of this elimination, you could have solved this equation right here for x squared and then plugged it in there, or solved this one for y squared and plugged it in there. Okay, now that I know what x is, I can find out what y is, because L squared minus x squared minus 2y squared equals 0. So this will be 2/3 L squared equals 2y squared. So L squared over 3 equals y squared. So y is L over the square root of 3. And then z, you can work it out, but it must be the same thing. You think? Well, we better work it out. Where's my equation for z? Oh yeah, z equals, z squared equals L squared minus x squared minus y squared. So L squared minus L squared over 3 minus L squared over 3. So L squared over 3. Okay, so there's the dimensions of the box that has the greatest volume, whose diagonal is equal to L. So it comes out to be a square cube box, which should be no surprise because they're usually the maximum, unless you're missing a top or something like that.